Today we will continue discussing the instability in plasticity, but the configuration is little different. So this time we are talking about thin-walled tubes. Okay, so now before going into the detail, mm, I want to use certain result that we are about to discuss. I mean the theory part of that, which belongs to Levi-Mises theory or so-called Prandtl-Ross equation. We are not going to either derive or discuss that today, which should have been by now. Uh, but I'm just going to use one result, and that result is the change in plastic strain, as in, you know, the entire matrix differential change is proportional is proportional to the deviatoric stress. Okay, so this is one result that you use in our calculation. Okay, uh, now let us say uh, we have a cylindrical pressure vessel. Now, this part, what I'm about to discuss, must be familiar to you from your undergrad lessons. Okay, so imagine this is a pressure vessel. Okay, right. Currently, I'm showing it to be of arbitrary shape, but soon bring our attention to cylindrical pressure vessels. So in that, I'm taking a differential element, and that differential element, okay, so let's say it is subjected to um, so it is subjected to so-called hoop stress and longitudinal stress. So this one is the longitudinal stress. Let's call it sigma 2, and this one is sigma 1. Okay, so now you see the pressure vessel has certain curvature, and each side of this differential segment can be shown to be a part of a circular arc. If it is really tiny, then can be shown to be a part of a circular arc. Let's say this radius right here is r1, and this one is d theta 1, this differential angle that it subtends about the center of this side right here. Now you can imagine that this line is so drawn that it is perpendicular to this side as well as this side. Okay, same thing to all the other corners. Now if I take the normal from this corner. Okay, let's just keep the corners and name A, B, C, and D. Now let's say if I do it from corner D and get that normal, let's say that normal extends and intersects with the normal at A, um, at another center O2. So that is basically the center of the circular arc AD. Okay, if it is really tiny, then it can be shown to be a circular arc, and let's say that subtends an angle of d theta 2. Okay, now let us draw the free body diagram, and this is not the free body diagram. The free body diagram of the differential element. So you have your usual sigma 1. Now we know for a fact that these are principal stresses. Okay, and so we are writing them to be sigma 1 and sigma 2. Uh, Ideally, we should not be, but we know that these are the only components that we can imagine for a thin pressure vessel. Okay, if it is really thin, you can let go of the shear components because the thin cross sections cannot handle shear components. So, so you can imagine that these are the two principal stresses that are involved. And of course, there would be another principal stress, okay, which is normal to the plane, which basically is on the bottom surface. On the bottom surface, it is the pressure on the bottom surface. Okay, it is the pressure P that is acting on this differential element. But you'll have, if you really think about it, if you make a comparison with the thick cylinder, uh, it you need to understand that with that thinness of this element, now I'm showing the thinness of the geometry. So on the top surface, the sigma r term is 0. On the bottom surface, sigma r is minus p. Okay, and that change is happening rapidly over this thin cross section. Okay, uh, so now you like to see how does this third principal stress, okay, compare with the other two. Uh, so this is how it compares. Let's try to write the equilibrium equation in the sigma r. So I mean radially outward direction. If I sum all the forces, so at first this sigma 2 is so of course there is this outward force which is p times r1 d theta 1 times r2 d theta 2, which are basically the side lengths. So AB equals CD equals R1 d theta 1, and AD equals BC equals R2 d theta 2. Okay. So of course the force due to pressure is acting outward. Now you see these are the sigma 1 components. So on either side, that if you really think about it, this is the thin cylinder as seen from this side. So this is O1, this is R1, this is d theta 1, this is sigma 1. Okay. So first of all, sigma 1 is acting. So if this is the direction of the pressure, I can imagine that divides this into d theta by 2 and d theta by 2. So this is where the pressure is acting. So the sigma 1 is acting on CB and dA. Okay, and let's say the thickness is T. So T times R2 d theta 2 is the area on which sigma 1 is acting. Now this angle is also d theta by 2. These are not arcs. The sigma 1 and sigma 2 are shown with straight arrows. D theta 1 by 2, d theta 1 by 2. So sigma 1, so this is the area times sigma 1 times, so 2 times because it is in the either side, and then you are supposed to multiply sine d theta by 2, d theta 1 by 2. Okay. Similarly, twice t r1, the same thing you can do with sigma 2, d theta 1, sigma 2 sine d theta 2 by 2. And in the limit d theta 1 and 2 tend to 0, this expression essentially becomes, so this is a 0, right? So this basically means uh, d theta 1 d theta 2. Okay, so this becomes your d theta 2 by 2, and this becomes your d theta 1 divided by 2. So in the end you can write p times r1 r2 minus sigma 1 times t times r2 minus sigma 2 times t times r1 equals 0. Or in other words, if I divide either side with this quantity r1, r2 and t, I have p divided by t equals sigma 1 divided by r1 plus sigma 2 divided by r2. Now imagine that t is much smaller than either R1 or R2. That's what makes it a thin walled tube or thin walled pressure vessel. Therefore, the pressure itself, okay, which is one of the principal stresses at one of the boundaries, is much small compared to the longitudinal and the hoop stresses. Sigma 1 is called the hoop stress, and sigma 2 is called the longitudinal stress. So this basically also means that P is much smaller than sigma 1 and sigma 2. You can imagine if T by R1 or R2, let's say, is 10 to the power minus 2. So this pressure right here is of the order of 1 in 100 of either sigma 1 and sigma 2. And that's a tiny principal stress, and most of the time we would be neglecting the sigma r because it is either 0 or much smaller than the other two components, that is sigma z you can call it, and sigma theta. So sigma theta is basically your hoop stress. Now we need this expression. Okay, and can you tell me if this equation is valid outside elastic limit, or is it only valid within elasticity?
Sir, within elasticity.
So this is an equilibrium equation. So everywhere it is valid.
It is valid everywhere. Yes, correct. That the reason is this is coming from, or this itself is the equilibrium equation, and it doesn't care about your constitutive relation. How the strain is changing with stress, it doesn't bother. So it's just the equilibrium equation. Okay, so that is going to be universal for us. uh, Acha, in last week when we did thick pressure vessel, we showed these two pressures, P prime and P double prime. P prime is when the yielding is initiated in a thick pressure vessel, and P double prime is the maximum load bearing capacity of the thick cylinder, which basically means that the entire cross section has turned elastoplastic. Okay, and that thing we did with elastic perfectly plastic material model, and we did uh, mm, uh, an example with various segments in it. One of the segments were to show that mm, if the T is much smaller than the R. Okay, now here you had one internal radius and one external radius. I'm talking about the difference between the two, and that difference, if it were much smaller compared to the average radius, we showed that, or rather, if these two are very close to one another, then in that case, we showed that this P prime and P double prime are very close to one another as well, which basically means going from yielding at one of the locations to having the maximum load bearing capacity. Okay, that is a very tiny change. Okay, so and that assume with the assumption of elastic perfectly plastic material model. Okay, I mean, if it is in the limit when T tends to 0 or T by R tends to 0, these two pressures are essentially the same pressure. I mean, by the time there was an initiation of plasticity at the inner surface to the pressure by which makes the entire cross section plastic, that is just that is essentially the same pressure. Okay, so the entire cross section turns plastic at the same pressure if it is really really thin. Now, of course, when we are talking about thin pressure vessel, we cannot work with this type of material model. And as you have seen in the last class as well, we were talking about hardening. Okay, that is, even if we plot stress with plastic strain, that is what it is supposed to look like. Okay, this is sigma y. And if it were to be plotted against the total strain, so this is what it looks like. So this part right here is elastic, 1 is to E, and then there is yielding and the hardening and so on. We showed there is a tangent modulus and so on. Okay, so all of so we need this type of a material model when we are dealing with uh, a thin pressure vessel. Okay, uh, I mean, these two are not different materials. Okay, it's the same material, but now the material needs to be modeled like this. The material can no longer be modeled like this. Okay, of course, the slope of the stress strain diagram in the plastic part is quite small compared to the elastic part. Okay, and that's why this type of flat uh, mm, plastic portion can be justified, but that doesn't mean that can find a universal application. I mean, it's still a model. Both of them are models, but this model is more accurate, and we need to go for a more accurate model. Without that, essentially, this means that the moment you have your yielding, okay, you also have your ultimate point. So we are talking about instability, which deals with sigma ut, which in essence, so we sorry, not sigma ut, sigma u, you can call it the ultimate stress. So in the last class we saw the example of ultimate tensile stress. Here, you see, even with the previous set of examples, when we talked about the maximum load bearing capacity, be it elastoplastic bending, torsion, or thick pressure vessel, so in either case, when we talked about that maximum load bearing capacity, that in essence was corresponding to your some sort of ultimate stress. Okay, that essentially, ultimate stress is what? Again, it is the maximum load bearing capacity. So, mm, uh, So here also, when we are talking about thin pressure vessel or thin walled tubes, thin cylinder, there also we are trying to arrive at an ultimate stress, that the maximum stress that you can apply. And so that also, uh, but as we discussed, if we were to model the stress strain diagram as flat or elastic perfectly plastic, then we would end up getting a situation where the yielding stress is also the ultimate stress. Okay. uh, Now this time, uh, so that's why we need a stress strain diagram with a hardening curve. That's why you need to model the material behavior with its proper hardening. Okay. So that's what we would do. Okay. One more thing to notice is that as a thickness or thinness becomes really small, um, it is more or less the uniform stress across the cross section. Okay. uh, of course you can argue that on one side there is no pressure, on the other side there is pressure. So of course that is there. Okay. But pressure is a much smaller stress component as compared to the other stresses that also we discussed. So more or less the stress state is uniform across the section. Acha. So with all that discussion, let's move on to uh, let's move on to the case of elastoplastic deformation of the thin walled tubes. Okay, so here we are dealing with a cylinder, which basically means as long as hoop stress is concerned, so this radius right here is, let's say, r, but in relation to longitudinal stress, r1, that r2 is infinity, which when you plug into this equation, sigma 1 is which is also sigma theta. We know for a fact that the sigma theta is a the theta direction is a principal direction, and sigma 1 is sigma theta. Okay, that's what we know for a fact. Again, with thick cylinder, we came to know that sigma theta is greater than sigma z is greater than sigma r, right? So we knew all of that. So yes, this is sigma 1, no doubt. So this is sigma 1 and this is sigma 2 for sure. And that just happens to be P times R divided by T. Now, is there any hope for sigma 2 or sigma Z that is in the longitudinal direction? Yes, there is. So you'll have to imagine that, in order for this to be a cylinder, this end is closed. Okay. So, so if I take 1/2 of the cylinder, so there is sigma Z acting through the thin cross section of it. Okay. So how much force is it applying? So twice pi r, which is the circumference, times the thickness, which is the area, times sigma z. Okay. And that much is pulling downwards, and what is pulling upwards is again the pressure. So P times pi r squared. So this time I'm just summing all the forces in z direction. So P times pi r squared is the force that is going in positive z, and this quantity going in the negative z. Okay, and that basically gives us sigma z equals P r divided by 2t. So exactly half of sigma theta. Okay, so and sigma r, of course, much smaller than sigma theta and sigma z, as we discussed, and for all intents and purposes can be neglected. Okay, or could be taken as zero. So we also need this information right here. So basically what we see that sigma theta is twice sigma z, and when it comes to thin cylinders, suddenly we thought, instead of using the Tresca criteria, using the von Mises criteria would be a good idea. Okay, and then we came up with the von Mises equivalent stress, and the von Mises equivalent stress is 1 by 2 sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared. Okay. So can you write the expression for sigma equivalent in terms of P, R, and T? So substitute the expressions for sigma 1, sigma 2, and sigma 3 in this expression and get the expression for sigma equivalent.
Root 3 by 2 PR by 2T.
So if I were to write like this, P equals T times R times sigma equivalent, what else comes here?
Two by root 3.
Is it turning out to be 2 by root 3?
Yes, sir.
Okay. Okay, so we need this expression. Now, now the equivalent plastic strain increment, this has the following expression. You might ask, why so? Why the coefficient is such? Uh, for that, try this. Let's say for uniaxial. So everything equivalent is in comparison to uniaxial tension. So in uniaxial tension, stress components are like this: sigma x 0 0 0 0 0 0 0 0. Okay. So can you write the expression for the deviatoric stress? So deviatoric stress, so yeah, just try it with. So we are taking the example of uniaxial tension. So in that, sigma equals, or let's say sigma 1 is sigma x, and sigma 2 equals sigma 3 equals 0. So how much is the deviatoric stress? Okay, and since the differential plastic strain is proportional to the deviatoric stress, this means d epsilon p2. Okay, sorry, I should be doing this differential quantity and also only the plastic component. So since the plastic strain increment is proportional to deviatoric stress, so this second and third principal differential plastic strains are essentially half and negative of the first component. You see, this is minus half of S1. That's how the proportionality works, right? Now, I hope you can, get why sigma 1 is sigma x, sigma 2 is sigma 3 equals 0. That makes S1 equals twice sigma x by 3 and so on. Okay. I think you can do that. So, or if you have forgotten how Deviatoric stress works, you can revisit that. Okay. Now, this everything is in relation to uniaxial tension, and this is not uniaxial tension. This is very much biaxial stress state. Even if you neglect sigma 3, it is biaxial stress state that is happening. Okay. So, but this thing I'm just doing to show that this is the coefficient you are looking for. Okay. So when I try to get the equivalent, so when I do this, d epsilon p1 minus d epsilon p2 whole squared, then I'm just, the term within the square bracket. That's what I'm trying to do here. Okay. So write this expression in terms of d epsilon p1 squared. Okay. Just check what coefficient do you get. What is the coefficient that you are getting?
It's a 2.5.
No, absolutely not. You see, d epsilon p2 minus d epsilon p3 should be 0. Okay, so one of the terms is not required. But take any other term, so it is you are subtracting something from a negative quantity. So you are basically adding. So it is 3 by 2 whole squared. And this is also 3 by 2 whole squared. So 2 times 9 by 4, which is 9 by 2. I don't understand. I mean, what else will you struggle? I mean, this simple, addition and multiplication and taking a square. I'm not asking you to derive anything. I'm not even asking you to remember the expression for Deviatoric stress. Okay. So I'm just trying to understand the what is the lowest limit that I can expect from you. But that keeps lowering day by day. So that coefficient becomes 9 by 2. Okay. Now to this whole thing, if you multiply your coefficient 2 by 9, okay, so this whole thing gets multiplied with 2 by 9, and when you take the square root of that, you essentially get the absolute value of the plastic strain in the x direction. And why is that significant? Because essentially when in an uniaxial test, you are plotting sigma x versus epsilon x. And as we discussed, the majority of the strain is plastic strain. So since you are plotting sigma x versus epsilon x, you would want the equivalent or the differential equivalent stress, okay, to be same as that of the x component. Uh, so that's what is being done here. Okay, to so that is how you define the equivalent plastic strain increment, so that it conforms with uniaxial tension. Okay, so this is the expression for the equivalent plastic strain. So we also need this expression. Okay, now the rest of the things we can erase. So we talked about having the expression for equivalent plastic strain. Now, as you can see, that if I am only comparing the plastic strain, sorry, only comparing the principal component. So assuming that we are doing everything in the principal coordinates, and that we are, since sigma that is the directions r, theta and z are principal directions, so everything that we are doing in the principal coordinates. Okay, so instead of writing them as 6 components, we can simply, I mean, 3 normal and 3 shear we can do that in all with principal stress and strains, and that's what, let's say, we are doing. So this divided by S1 equals this equals this, right? So that is for any general purpose. But the earlier example that you saw with is what is with your uniaxial tension, but that is only to get the coefficient that comes in front of this square bracket. Okay. This time we are comparing the situation with with the case in hand, that is thin wall tubes. Okay. Now, can you write S1, S2, and S3 in terms of sigma 1, sigma 2, and sigma 3? What is the relation between S1 and sigma 1 and sigma 2 and sigma 3? Okay. And accordingly write the expressions for S2 and S3. And then substitute the expressions of sigma 1, sigma 2. Okay. And sigma 3 is much smaller than sigma 1 and sigma 2. Okay, you see, you can write it like this. There is sigma 1, then sigma 2 is sigma 1 divided by 2, and sigma 3 is much smaller than sigma 1. So write it like this. So in the end, I need you to give me the ratio So please remember, uh, epsilon 1 basically means epsilon r, epsilon 2 basically means epsilon theta, and epsilon 3 basically means, sorry, sorry. This is r, this is z, and this is theta. কি করা যায়নি এখনো? এই পার্টটা ক্যালকুলেট করা যায়নি?
Sir, 1:1.
কি করে 1:1:1 এলো তোমাদের, আমি তো বুঝতে পারছি না। You see, S1 is approximately, or S1 is like sigma 1 divided by 3 times 2 minus half, which makes it sigma 1 by 2. S2 is twice sigma 2 divided by 3 minus sigma 1 divided by 3, and of course sigma 3 is 0, nearly 0, or much smaller compared to sigma 1 and sigma 2. So this expression tells you that S2 is again sigma 1 divided by 3, then twice sigma 2 is sigma 1, subtract sigma 1 from that, so this goes to 0. মানে এতটুকু করার ক্ষমতা নেই। Then this, so in that you can uh, see that this becomes 1 by 3 sigma 1 plus sigma 1 divided by 2, which makes it minus sigma 1 by 2, which is minus S1. And you might recall that S1 plus S2 plus S3 has to be 0. So if one of them is 1, one of them is 0, then the two are negative of one another. So the ratio is 1 is to 0 is to minus 1. Okay. So we need this information as well. Now substitute that expression. So please note, here we have a situation where it is plane strain. The strain state is such that there is only strain in radial direction and theta direction. There is no strain in z direction. You might recall that in a thick cylinder case, we also took into account among many situations, we also took into account the plane strain situation. The justification for the plane strain situation comes from here. We didn't choose this to be plane strain, but by the very definition, uh, or but by the very nature of the the differential strain, it turned out to be plane strain. Okay, so in z direction the strain is negligible. So you can now substitute these expressions. Please understand, this means d epsilon p3 equals minus d epsilon p1. This doesn't mean d epsilon p1 equals 1 and d epsilon p3 equals minus 1. Okay, so that's what I need you to substitute over here. And also this equals 0. So substitute this over here, and get this expression, get the expression for the equivalent plastic strain in terms of d epsilon p1, or for that matter theta.
Two by root 3 d epsilon on p.
2 by root 3.
Yes.
So this is our next important result. So now we are talking about a situation where you have reached the limit on how much pressure that you can apply. That is instability. That is the ultimate point. So for that, I'll have to set the derivative of P to 0. Now if I take the derivative, okay, so please recall, sorry, take the derivative of this whole thing. Okay, you see, once there is pressure and as the cylinder expands, the radius changes. As the cylinder expands, the radius changes. Okay, so the radius is changing, and since the radius is increasing, okay, so this circumference would be increasing. Okay, and then the thickness has to reduce, because you see, plastic deformation is volume preserving, isochoric. Okay, so the thickness reduces, so everything changes in here. Okay, so the thickness reduces, the radius increases. Okay, so take the derivative accordingly. What expression do you get for the derivative of the right hand side? The first one is obvious, which is T by R times d sigma equivalent. You can also think in this way, since epsilon z is 0, so R times T is a constant. Okay, so accordingly also you can take derivative, but you know, you can take also the derivative continuously. Okay, so if I were to divide either side with this quantity T by R, then I have, or for that matter with 2 root 3, then I have okay, and that equates to 0. Now, would you agree that epsilon d epsilon theta is essentially dr divided by r? You see, if there is a tiny change in the radius, and now it has become r plus dr, so this is a new circumference. So the circumferential or theta directional strain, okay, because it's a differential quantity, the differential strain can be defined as this minus this divided by this. So essentially this turns out to be dr divided by r, and this is a positive quantity because the radius is expanding. Okay, and you can also check the sign. S1 is greater than 0 and S3 is simply minus S1. So this quantity is positive. Okay, and this is your epsilon d epsilon theta. You can also call it plastic d epsilon theta. Whereas dt divided by t essentially represents how much the thickness is changing per unit thickness, which is the epsilon r. So this quantity is your d epsilon pr, and this quantity is your d epsilon p theta, or this quantity is your d epsilon p 1, and this is d epsilon p 3, but that is simply minus d epsilon p 1. Okay, so with that you can write D sigma equivalent equals sigma equivalent times twice d epsilon p 1, okay, or d epsilon p theta, whichever you want to call it. But that makes it, you see, twice d epsilon p theta is 1 by root 3 d epsilon p equivalent, or in other words, d sigma equivalent d epsilon p equivalent equals 1 by root 3 sigma equivalent. Compare this to the last class's result where in uniaxial elongation, uniaxial tension, the maximum load bearing capacity, the ultimate point would appear wherever this was true. So this is in uniaxial tension. And this happens with thin pressure vessel under internal pressure. So the general expression for instability is sigma equivalent prime, which basically means this derivative, 1 by z sigma equivalent. Okay. Now this z could be taking different values. In this case, 1 by root 3. Sorry, z in this case is root 3. Okay. Now it's only you can tell whether you understood all of this or not. But in my mind, you have not gone through, or you can't recollect many of the things that we discussed in the most of the things that we discussed in the previous set of classes. So I hope you go through all of them, then probably you would understand any of this. Okay, or maybe you understand all of this. I don't know. So, but that is the derivation, right? So this is the general expression. Okay, and now I just would give you one assignment, and with that we can end the class.